I had looked very much forward to meeting and discussing with all of you in Santa Barbara, but unfortunately, a fractured ankle is keeping me home 9 time zones away. So let's get started, please. Next slide. Hello? Yep, okay, good. Okay, so we started in CARMENES actually in a competition. Carla Alto Observatory had asked for a 5-year key science project with their 3.5-meter telescope. Next point. There were actually 2 proposals, one coming from German side and one from the Spanish side for visible and near-infrared spectrograph. Next. We patched together the funding with contributions from all 11 partners, including the observatory. Next. And signed the construction agreement in 2011. So next slide. So the first thing we had to do was to create a consortium, which means building trust amongst partners. And that means getting to know everybody's strengths and limitations, admitting to your own. And that really enables engineers from different institutions to work with each other. Next. One important point there that I thought was something to find our way in was keeping emotions out of trade-offs. When you talk about different design possibilities, one shouldn't get emotionally too invested in one's own ideas and be open. That's an important point for working together. Next point. And of course, you need to get to know each other, and having fun together really helps to get the consortium spirit up. Next point. So in systems engineering, keeping specifications simple. In CARMENES, we decided very early to build it for precise RVs and not to allow any other science drivers. Next point. Even if you are not forced to it, having external reviews and having good reviewers is really an important aspect of getting the best solutions. And that was very helpful to us. Next point. And by and large, we tried to have conservative solutions wherever possible. There are enough things in precise RVs that are really hard. So things where known technological solutions exist, you should take the known solutions and not experiment on those things that where it's not really necessary. And sometimes making choices for the second best option, but a safe option, may be better than taking on too many risks. For instance, we did that with our detector choices. Next slide, please. So there is this famous triangle of cost, risk, and schedule. You can pick 2 of these, and the third one is set. You cannot optimize all of these 3 at the same time. Next point. And in that respect, you need competent project management, and maybe you have to pay for it. We did this actually with external help, but that is definitely worth the money. It worked well for us to have some professional project management in this. One lesson learned is that most time is really lost early in the project. It's very difficult to catch up later on. In the early phases, there is a real risk of losing time, for instance, to things that go slow in the administration. Next point. Yeah. We had one big advantage, namely we could get a lot of observing time. Our initial allocation was for 600 usable nights plus 150 if everything worked well, which it did. So we started with an allocation essentially of 750 usable nights. And it still turned out that finishing a systematic survey is hard. We are still working on finishing our 300-star survey, partly because we also wanted to do some other science. But having regular observations means that you get better calibrations. Having gaps certainly doesn't help. A very important aspect also is the cadence that you can get. Next subpoint. So cadence and sampling are very big issues. We are looking for planets around M dwarfs with typical periods of a few weeks. So not having to deal very much with scheduling. We had so many nights that most of the telescope actually was scheduled for us for quite some time. That means we could really sample those few week RV curves quite well. And clearly this will be more difficult for planets that have periods of about 1 year, but still not being just a bright time instrument clearly was very advantageous for us. Next point. Also, flexibility is a big bonus. Having many nights scheduled in advance was quite nice for scheduling transits and also for doing transit follow-up for tests, for instance. We could just use the time that had already been allocated and switch one additional target into our observing list. Next. Yeah, so the spectrograph is alive. The spectrograph does not stay the same once you put it on the summit. And here is a curve that shows the raw RVs, that is the drift of the spectrum on the detector or our near-IR channel over time. You see that we got rid of some initial problems quite nicely. Then it was stable for some time and suddenly it started acting up. We understand what happened. There was a problem in the cooling system, which we couldn't fix immediately, partly because of the pandemic. But this underscores the importance of keeping an important technical team. Next slide. So one needs to keep this team going, and the mountain staff here is key also to the success. We made the people on Cala Alto part of our team, and that helped us to get quick feedback, to have them involved, to solve small problems on the spot, and to keep the information flow going. Next point. Also, there are, of course, people needed at the home institutions, partly postdocs, who are responsible for the software, for doing software upgrades, quality assurance, health monitoring, and so on. And this is something that needs to be that needs attention in the consortium to give some first author papers also to those people who are doing service work. And maintaining engineering competence, clearly this is difficult in cases where there are pressures on the time of engineers, but one shouldn't leave the too early and think the instrument is on the mountain, it's working nicely, now we can go home and leave it all to the scientists. Next slide. So there were some bad surprises. One initial surprise perhaps was that administration in general can be a big schedule risk because getting signatures can take extremely long. Next point. Then another bad surprise later on, a technical surprise, was that thermal leaks are always bigger than estimated beforehand. Keeping heat keeping heat from flowing into the optical bench is more difficult than we thought, and I think this is an experience that some others also have had. Next point. Yeah, as we have already heard that hollow cathode lamps have problems. We were a bit caught by surprise by how bright the emission lines are in the red. So a lot of bleeding problems that we hadn't fully appreciated before actually starting to test our instrument in the lab. And there are aging and quality issues. Next point. We had planned on actually mitigating those hollow cathode lamp issues by windowing the detector and read out windows quickly where the lines are. And that really didn't work very well. So we had to go back to a detector readout mode where all the pixels are treated the same. And that means we basically had to give up on the idea of using simultaneously the hollow cathode lamps and switch to a scheme that uses a Fabry-Perot. Next slide. Oh yeah, and a pipeline is no jackknife. We have a very nice pipeline, and the pipeline does a number of things very well. Especially it produces lots of auxiliary data, indicators of radial velocity as a function of wavelength, the full width half maximum of the lines. It produces activity indicators and so on. That's very good and actually necessary. But for actually debugging your instrument, you would like a more flexible tool than a pipeline that works nicely once you have decided which type of data you really need.
Yes, 1 minute left. Yep,
there are a few things where we had near-death experiences. One was, our biggest issue was that there was a threat that the observatory might get closed in 2013 due to the financial crisis that hit the funding agencies funding the telescope, and we managed to keep going with strong consortium commitment and some outside political help. Next point. And also, we had to take some shortcuts in our assembly and testing and verification of the instrument because there was very severe time pressure. We had to gamble, and we got lucky in the sense that it worked. Next slide, which is also the last. So the main success factors was we started with a very clear scientific objective. Next. And we had carved out a well-defined scientific and technical niche that was not occupied at the time when we started. And we, for some time, we were quite unique in the things that we were trying to do. Next. We had a very committed consortium. Next. Part of that was that we, from the very beginning, decided to have a joint science program and to write joint publications and work together as a consortium, both on constructing the instrument and on exploiting its science. Next point. Yeah, the institutes in our consortium had strong and complementary technical and scientific expertise. Next. And last but not least, this I think was one also of the factors that contributed to having everything running quite smoothly, was to get excellent support from the observatory and include the observatory in the collaboration from the beginning. Thanks, and sorry for the slight technical issues.